Good afternoon. Welcome back. My name is Roger Ganem, and it's my distinct pleasure to introduce our speaker for this afternoon's keynote lecture. Professor Julio Ottino is a professor at Northwestern University in the departments in the schools of Engineering and Applied Sciences and the School of Management. Prior to that, or backtrack, he had served 17 years as the Dean of Engineering at Northwestern. I was told to be short in my introduction, so I'm going to summarize the several pages I had in notes in very few words. Professor Ottino is a member of the National Academy of Engineering, the National Academy of Sciences, the US Academy of Arts and Sciences. His fundamental contributions in complexity as reflected in the physical sciences, starting with mixing to granular flows, was subsequently extended to analyzing and exploring complexities in brain systems, educational systems, learning paradigms, and for that he has received a number of awards from the National Academy of Engineering. And without further ado, I will yield the platform to Professor Ottino.
Well, thank you, Roger and Ajit. I love giving talks and explaining things, okay? So I was delighted to have been invited to give this talk. Is the first slide on? I can see them here. So I gave a title, not knowing exactly what the content was going to be. Let me see, is there? Okay, perfect. So the title is very general, Thinking That Connects Domains, Evolution of Ideas Across Art, Math, Science, and Technology. And hopefully a few things, there are many things that you know that I will say. A few things will be new. I think the overall arching lesson of the talk is that lessons appear when you see things in parallel. And I will have a very coarse lens, starting way back when Galileo. And then at some point, I will focus on maybe 3 people in parallel. That may be new for some people. And I will address throughout this creativity, especially visual components. And then I will finish with some observations about the present, okay? Now, you cannot see this clearly. It's supposed to be in parallel 3 columns of science on the left, technology in the middle, science on the right. In the black part, there is even a column about art. And a lot of what I'm going to say, you can find in pieces that I have written in that website, okay? Now, the whole talk will be about explanations, and some people have been very emphatic on the value of explanation. G.H. Hardy, who was one of the most famous mathematicians in between the war in England, said that there is no scorn more profound, on the whole more justifiable, than that of the men, and at that point they were all men in math, who explained and said exposition, criticism, appreciation for second-rate minds, okay? Now, but there are good people, like Chandrasekhar, not very far from here in the University of Chicago, who really decided to explore the thinking modes of Shakespeare, Newton, Beethoven on creativity, Nobel Prize physics. And this is by no means new. People like Da Vinci argue that art and science are equally valid modes of investigating the world. And he put painting as one mode of inquiry. So I'll start quickly with what kind of thinking modes operate in this domain. So if you have science, kind of more analytical, rational, logical, left brain sort of thing. Technology and art more metaphorical, creative, divergent. Technology is always in the middle between art and science, and in that book that I referred, the whole point of the book is why this happens. So in science, the verb that goes with science is discover, that's a mode. Technology is invention, and art, this is more debatable, is creation, okay? Now, you can ask, what does math, many people in here are, there's an underlying component of math, and mathematicians are not shy in expressing how much creativity there is in math, and David Hilbert, one of the greatest mathematicians of the last century, when asked about a former student how he was doing, he said, well, he did not have enough imagination to be a mathematician, but he's now a poet and he's doing fine. Okay? So math, if you want to put math in that spectrum of art, creation, invention, mathematicians are equally divided of putting art in discovery. Theorems are there, you just discover them, but it's part creation, and then applied math will be in between, traversing both. Computer science will be, the theory part will be more like pure math, discover, but there are people who have written books equating computer science and artistic pursuits. There's a book, Hackers and Painters, for example. And engineering, by the way, clearly covers science and technology, but if you start putting design, it covers the waterfront. With design is everything there. So in this timetable that I had put in there, I start at the top when Thomas Hobbes visited Galileo in Florence, and people in social science, they have always been fascinated by building a theory of how societies work, and Hobbes did such a thing. He did a book on how physical phenomena could provide a glimpse on how societies evolve. And that was way, way at the beginning. And you can see that amplified a little bit. So this will give me something to talk about the first part of creativity. And in this first part, I will start with kind of Newton. And there are many people who have expressed opinions on this topic. Kant, for example, who, in spite of being one of the greatest philosophers who ever lived, I agree with him. He put the creativity emerging from Newton's work on a lesser plane than Homer and writing, because he thought, he argued, and many of you will not agree with him, that in Newton you could see the steps that he took going from one concept to the other one, okay? So he put artistic creativity on a higher plane, and that kind of arguably not the case, at least for me. But then there are people who took things to the other extreme. So when Lagrange, part of his career was in Torino, in Italy, then he ended up, well, in Russia and then in France. Many of you may know the quote that in his work in analytical mechanics, he proclaimed that first weaken the argument, so he said, you shall find no images in this book, okay? And the same thing goes for people like Laplace. And the people who would be on both sides of the spectrum, this was analyzed by people like Gerald Holton, a historian of science in Harvard. On the non-visual side, you'll put Lagrange, Heisenberg, who thought that pictures weaken the arguments in quantum mechanics, Cantor, with his infinities, and Weierstrass, but the part of people who are on the visual side is equally illustrious, if not more. Hilbert, Einstein, Poincaré, Feynman, Riemann. But the person that I want to focus more is on Maxwell. So it's hard for anybody to comprehend everything that Maxwell did. He died at 48. Einstein had 3 portraits in his office in Princeton. Faraday, Newton, and Maxwell. And he was asked on what shoulders he had stood. He was very clear that it was on Maxwell's. So Maxwell, he was, and this is a quote from Einstein on the centenary of Maxwell's birth, is that physics changed completely after Maxwell, okay? So mechanics dominated, and then electromagnetism came and augmented the picture, okay? So he contributed to electromagnetism, geometrical optics, kinetic theory. The birth of statistical mechanics would have been enough to be famous. Mechanics and structures, many of you will know what he did. He uncovered the structure of the rings of Saturn, and he produced even the first color photograph ever, okay? And this is a quote from Einstein about Maxwell. The conception of reality that he brought was the most profound and fruitful that physics has experienced since the time of Newton. But the main reason that I bring in Maxwell is that Maxwell talked, and many people have written papers. He gave a lot of ammunition for many people in philosophy because he talked about physical analogy. And in there you have a paper coming from Studies in History and Philosophy of Science by Alisa Bokulish, and another one on Maxwell and the method of physical analogy. He drew lots of pictures to get to the concept that he wanted to explain. And for example, the picture on the left is when he was throwing ideas on how electromagnetism would evolve, and he had a mechanical sort of picture of how the ether will look like. Eventually, the picture disappeared, and he was replaced by the equation, really. But this is the crutches that he stood on in developing the theory. And then he wrote a few papers on mechanics that many of you will know, maybe 2 or 3, but I know, and I wanted to give a little bit of publicity to a book by Bill Baker. Bill Baker is, with Adrian Smith, is the fellow who did the Burj Khalifa, 2 local boys from Chicago. Bill is a good friend. And this book, The Geometry of Equilibrium, James Clerk Maxwell and the 21st Century Structural Mechanics, this book is going to appear published by Cambridge University Press. The fellow of them, Oschendorf, many of you will know, he's a MacArthur fellow. So I have seen part of this book, and this is coming. And a lot of what Bill Baker and his collaborators are doing is building on ideas that came from Maxwell. These are some of the pictures and plates from papers. And you have to recognize these pictures are not from Maxwell, they are from Bill Baker in some papers, that there is a beauty, a sense of balance in pictures like this. And this is what somehow has fascinated many people, including Bill. Now, about Maxwell, Peter Guthrie Tate, the one of Kelvin and Tate, I think he was 1 year older than Maxwell. He said that Maxwell preferred always to have a geometrical or physical representation of a problem. And Maxwell himself said that what gave him the idea of using this line of thinking was a paper that Lord Kelvin was probably 7 years older than Maxwell. He died afterwards, had a much longer life. And in a letter refers to the influence that Kelvin had with these geometrical views of equating 2 things in 2 different areas of science, let's say maybe propagation of heat and electromagnetism, and drawing from one to explain the other one. However, I think that Maxwell was selling himself short, because I do not know how on earth there is a geometrical picture behind this. The fellow on the left there, Adolphe Quetelet, was an astronomer, Belgian, who migrated into statistics, analyzing numbers from societies. He even wrote a book, Mécanique sociale. When a fellow named Auguste Comte heard about the name, and he said, wow, I was planning to use a name, he invented another name, and he invented the word sociology, Auguste Comte. But Maxwell was inspired by these people, social sciences, in arguing that for many, many particles, you could get away with averages. They were fascinated that the averages were constant. For example, there was an office in England that counted the number of dead letters. The number of dead letters were the letters that were incorrectly addressed and could not reach the destination, and the number was always constant. So I would say there is no physical picture behind this. You're dealing with statistics number. So how did Maxwell become Maxwell? So some people argue that a big influence on Maxwell was this guy, William Whewell. William Whewell was the master of the college where Maxwell arrived in Cambridge and was a remarkable guy. He was remarkably good coming with concepts. He invented the word physicist. As many, I will give you an example of one word. You think the word physicist has been there forever? No. The guy Whewell invited. Linguistic, consilience, astigmatism. To Michael Faraday, he suggested the words electrode, ion, dielectric, anode, and cathode. But he invented another word, and the other word had to do with this woman. Mary Fairfax Somerville was a remarkable individual, wealthy family. She could move in the highest levels of society, could interview the biggest scientists in Europe, France. She spoke fluent French, and wrote a book. I mention this because after this, I don't think you can get away. He wrote a book that was the biggest bestseller until Darwin, The Origin of the Species book came published by the same publisher. She summarized the entire body of science up to that point, okay? And Whewell wanted to review the book, but he couldn't use the term referring to Somerville. The preferred term was men of science. So he had to invent another word, and the word that he invented, believe it or not, was the word scientist. So the word scientist was invented to refer to Mary Fairfax Somerville. The challenge to invent the word had come from another writer, is there at the bottom. So these three people kind of coexisted. Somerville had a long life, Whewell shorter, and Maxwell even shorter, and Somerville couldn't cover Maxwell, let me see if I find it here, because this is when they lived. Somerville couldn't cover Maxwell because Maxwell was about 4 years old when he wrote the book summarizing everything. So it has lots of things about electricity from Faraday, but nothing after what Maxwell did, okay? So this is probably was the last possibility to summarize in one book all the aggregate of knowledge of science that exists in the world. So let's go back to the thinking modes of art, technology, and science. So if I show you anything that has to do with technology, even if you come from outer space, and I show you things and you ask me what they do, you can put an arrow of progress in technology. These are all modes of recording information, and clearly something that you put in the cloud now is more advanced than writing something with pencil and paper or in a tablet. Sometimes you see big jumps. I love these two things. They are in Milwaukee at the Harley-Davidson Museum. You see the 1912 bike with one cylinder, leather belt, and then in 1 year goes to 2 cylinders that we still have today and a chain belt. So in science, science has no use for dead branches. You build on previous knowledge. Once in a while, there is a revolution, like Maxwell, when he came with the equations of electrodynamic. In technology, you don't wait for one technology to die before you replace it for another one. So in science, it's a good idea to stand on the shoulders of giants. In technology, the only reason to stand on the shoulder of an elder giant is to crush the elder giant. You want to replace that technology with your technology. And in art, why art? Mentioning art because it's the most chaotic. And in art, I'm talking about modern and contemporary art. In art, it's a bad idea to stand next to anybody. Okay? You need to create your own DNA. Okay? So creativity, let me say a few words. Let's say that this set represents everything that is known about a given field at a given time. It could be all that is known about mechanics, okay? So sometimes you can combine two ideas in there and come up with a new idea. If the idea is big, maybe the boundary will increase a little bit. And I would call this combinatorial creativity. By the way, this is all that AI can do now, okay? But if the idea is really new, maybe there's a breakthrough, you break through the domain, you enlarge the domain, but it's still part of the domain, okay? This is different than what Maxwell did with electrodynamics. You had a whole bunch of things in mechanics, and then you have this other world. And I would call that a transformational creativity. That's a break with. You either break with the assumptions of the previous set and create a new one, let's say quantum mechanics from classical physics. Then you have no option but to say, now there is a new physics, which is everything. It's the classical physics plus the new physics. So let me give you two examples, and these are things in which you will know more than I do, but things that have been lying in there in this set, but it took someone to see it with different eyes to create something new. One is origami. It has been there for 1,000 years until people put math on it, and then at some point you have something that is called origami engineering, and you have ideas that can be deployed for aerospace applications and so on and so forth. The same thing goes for tensegrity. Tensegrity has been, the earliest reference that I can find is 1920. There is a sculptor in Latvia who did, there's a picture there on the lower left, tensegrity things. And the one in the middle is something that is in Washington. And then, if you're in material science, you say, wow, this gives me ideas. Maybe people in biology, they say, wow, biology has been doing this for a long while. We did not know this because we didn't have the lens to do it. And now the two are coming together, okay? So the only example that I have from my work that would be similar to this break with is mixing. So in mixing, everything is put in one blob, seeing where it goes, and depending on the definitions of the sets that you want in there, different types of mixing. But the where it goes is all based on continuum mechanics. You can follow the trajectories. And then you can have things like, if you have, I don't know, a coffee cup, and you know the position of every particle, and you move it arbitrarily and you wait to die, by definition, no, by a theorem, Brouwer theorem, you know that a point did not move before and after. It will be in the same location, okay? So all of this is predicated on diffeomorphisms, one-to-one mappings, so you cannot have one particle breaking into two or two fusing into one. And there are things that once you can build them, like these horseshoe maps, you have things that would fit within the realm of chaos, okay? What you have in there. And you have different classes. The horseshoe map, you don't break things. In the Baker transformation, you break things. And you can do experiments, and this is one experiment in which, if you are careful and you know where to put different blobs, you can see that one of them stays put, the other one produces these horseshoe maps and this chaos. And you can even study where these islands move, and this island is of period 1, so it goes back after one period. Now, after this, I went into granular materials, and you can use geometry to study granular materials, and this is some example. And not surprisingly, geometry takes you far on this, but at the top right, I have granular material in a circular container, and in this circular container, you can study the fluid flow in there, assuming that granular material is like a continuum. And with this, you can, by the way, the experiments that I mentioned before on fluids, those experiments could have been done any time in between when photography was invented up to now, okay? Of these experiments in a circle, the top rows, again, one is immersed in a fluid, the other one is dry. This could have been done any time between 1900 up to now. The bottom one, no, because involves computations. You know the theory on how this evolved, but to get all the results, you need the computations. And this is the part in which algorithms get into being, okay, going in there. So if you want to study how many particles behave in this container, and especially how they segregate, because the beauty of granular materials is something that makes them interesting. If you start with them mixed and you move them, they will unmix. So if you want to study how they unmix, you have the luxury now, which Maxwell didn't have, of following particle according to Newton's law, seeing what they do and so forth. And you can even feed this segregation model into a continuum model, and you could even study the competition between segregation, diffusion, and advection, and you can do three-way comparisons between theory, computer simulation, and experiment. And not surprisingly, if you want to do more theory of this, you go for the simplest possible thing, and the simplest possible thing will be to put the granular material in a maybe spherical container, and when you move it in one direction, you have flow moving, let's say, left to right, and then you change the axis and bottom to top, and you have things that look like this. And when you fill this in a container, I don't know if this will work or not. I give it a shot. If it doesn't work, no, it does not. So let me tell you what is that you should see here. So this requires a lot of visual imagination, because what you have is there a wedge that moves, and then is taken by the other flow that moves in the other direction. And essentially what you are doing when you are doing this is throwing the assumption that things cannot break or that particles cannot fuse. And when you do this, okay, before we said this cannot happen, and now I'm saying this can happen. And if you want to study this in very simple examples of what would be the consequences of this, you can build examples like this. These are called piecewise isometries. It's not that many people in math working in this field. And when you do this several times, you start getting pictures like what you see there. And when you put in the container, like what you have in there, there you see there's going to be a wedge that will move, and then comes in the other direction, it moves again, and you repeat this. You will get things that the picture with the triangle should have prepared for the degree of complexity that you can expect, and you get things that like this, that has names like exceptional set. They are what they are called fat fractals, because they have a dimension which is the dimension of the embedding set. And this is what it got us from breaking one assumption that led all the first part of my work in fluids when we went into solids, saying that something that couldn't happen, we let it happen. So these are the fat fractals. So we allowed this to happen, and we had this break with. And now we are in the age of algorithms. We couldn't have done this without the tools that we have now to really see things. But up to that point, everything that we see with our eyes, all the electronics here, the screen, the lights, everything, was designed because we knew the foundations, and we built them up, and we could predict things. And going beyond lights and electronics, the one who wrote a paper that was heavily, heavily quoted was Eugene Wigner. He was at the Institute of Advanced Studies, was a colleague of von Neumann. He wrote this paper about the unreasonable effectiveness of mathematics in physical sciences. And we are here. Algorithms, and then we're in the AI world now. And in the AI world, we basically can predict without understanding. People are trying to see how that can be done. It even has a mechanistic interpretability, is the name that they are giving to that. But in practice, you can predict without understanding. And that's a gigantic change on how science advanced since the time of Newton. Okay? So let's revisit creativity. I have this picture in which ideas coming from a set could be combined. You can come up with another idea. Lots of good things can be done within a framework. I mean, see how far a couple of axioms from Euclid took you in geometry until you exhaust the thing. And then maybe you can break with and you dispose of one assumption, one axiom, and you create different types of geometry. That will be a break with. But at the moment, where we are is you could fit the entire history of art prior to 1900, and you couldn't see it in that picture, but until 1900, all art, and I'm talking mostly Western art, all art was representational. And if you were in 1900, and you had AI as now, any AI that you want, and said, tell me what would happen next, you will not go from what is on the left to what is on the right. Okay? At the same time that physics evolved to quantum mechanics, art broke away from representational art and went into cubism and a whole bunch of things. So the fellow on the left, William Bouguereau, was the most respected painter in France prior to 1900, and now virtually no one remembers him, because what I have in there is Braque, but Braque and Picasso. So the question now is where we are, is, by the way, quoting Picasso. Picasso said, different time, different context, but the quote is still perfect. He said, computers are useless, he said. They only answer questions. But you know that in order to do something really great, you need the question. And at the moment, you cannot be helped with questions. The questions come from you. I would say there is no route yet for throwing all the assumptions. You could fit the entire history of physics prior to 1900. I doubt that you will come up with quantum mechanics, because who on earth will decide that energy is discontinuous, okay? And the other one is this idea of explaining itself. So we are entering a time in which prediction is decoupled from understanding. And you probably, many of you got a note from NSF about, basically they say, and I have one of my students went with Suleiman to Microsoft, former students. It's in the middle of AI in Microsoft, and they agree, this works, but we do not know why, okay? So NSF is investing money on this. As I said, there is science of progress, mechanistic interpretability. So let me recap and go into the beginning. So when I was invited to do a talk, I decided what to probably say and put together. And going in parallel with a few things is probably something that many of you may have thought, maybe not, but it's always enlightening to see things in parallel. In order to contrast how life was prior to Maxwell, I think nothing beats the example of Mary Fairfax Somerville, that she could write a book that summarized. By the way, you can still buy the book. It's still in there. You can Google this. It was even reviewed at some anniversary in Nature again. There's no way that you can put all together now, okay? But the contrast with Maxwell and Whewell and the creation of the world scientists, I wanted to have that. So the course lens was all the things in parallel, how Maxwell was affected by sociology, creating statistical mechanics. But then the focus lens was Maxwell, amazing visual imagination. William Whewell, who created Maxwell, and Somerville, who was reviewed by Whewell. And then I wanted to give you a sense of my view on creativity, the two components being combinatorial creativity, and you can do lots of great things in combinatorial creativity, but then the break with, and then these observations about the present with AI. So with that, thank you. And if you want to know more, you can Google these things. Thank you.